Welcome to the first lesson of the 7th module, which is on deflection of beams part 1. In fact, in the last two modules we have looked into several aspects of beam bending, how to evaluate the bending moment and shear force in a beam which is loaded, and consequently we have evaluated the bending and shear stresses in a beam. Now, while evaluating the bending stress in a beam, you must have looked into that we have taken the curvature of the beam into effect, and consequently we have derived the bending formula. Now, while looking into the bending formula, we have taken the help of the curvature of the beam, but as such we have not derived any equation for the curvature of the beam, or we have not derived any equation for the elastic curve. Now, in this particular lesson we are going to look into the differential equation and consequently the equation of elastic curve, and how do we find the deformation in a beam. In fact, the deformation which often we call as a deflection of beam is of paramount importance in our engineering application. You know, the beam member, when they are subjected to load, undergoes deformation, which we are terming as deflection when the axis of the beam moves in the vertical direction. Now, the question is, this kind of movement of the beam creates problems in our engineering structures. Say for example, the floor on which we are moving, basically they are supported on beams. Now, if for some loading the beam undergoes movement in the vertical direction, if it deflects, then the floor also deflects, and as a result it becomes unusable. That means, it becomes uncomfortable for the persons to use it or whoever will be moving over the floor. If you talk about any mechanical component, if it undergoes deformation, then there is a possibility that it will lose its alignment, and in the consequence there could be failure of the machine parts. Hence, it is very important to evaluate the deflection in a beam member, and it is expected that once this particular lesson is completed, one should be able to understand the concept of deflection of beams under different loading conditions. One should be able to derive the basic differential equation of the deflection curve. Also, one should be in a position to evaluate deflections in beams for different loading conditions. Hence, the scope of this particular lesson includes the aspects we will be looking into the previous lesson which we have discussed. It includes the concept of deflection of beams for different loading. It includes the derivation of differential equation and consequently the equation of elastic curve for beam, and also it includes some examples for evaluation of deflection in beams for different loadings. Now, let us look into the answers of the questions which we had posed last time. In fact, in the last lesson we had discussed aspects of shearing stresses, and hence we have the questions pertaining to that aspect, and the questions are related to that. The first question is, in a beam with rectangular cross section, what is the maximum value of shear stress and where does it occur? Now, this aspect we had discussed. Let us look once again that in a beam having a rectangular cross section of width b and height h, when they are subjected to loads and thereby the shear forces, they are subjected to the shearing stress, and the distribution of the shear stress is as this. It is a parabolic distribution having maximum shear stress at the neutral axis, which we call as tau max, and the shearing stresses at the outer surfaces, they are 0, and it varies in a parabolic manner, and the maximum shear stress is given by this expression, which is 3 by 2 V by A, and we calculate, if you remember, the tau as equals to V q by I b, where V is the shear force in the section where we are calculating the stress, q is the first moment of the area depending on at which section we are evaluating the stress. Supposing if we are evaluating the stress at this particular section, which is at a distance of y 1, then q is the moment of this particular hatched area with reference to the neutral axis, I is the moment of inertia of the cross section with respect to the neutral axis, and B is the width of the section, and this gives us the maximum value when y 1 equals to 0, which is at the neutral axis, and that is the value of the tau max, and thereby if we compute, it becomes 3 by 2 V by A. A is the cross sectional area, B times H. So, the maximum shear stress occurs at the neutral axis, and for a rectangular section the maximum value is 3 by 2 V by A. Now, the next question posed was that in a beam with circular cross section, what is the maximum value of shear stress? Now, this aspect also we have discussed in the last lesson, wherein we have said that we cannot use this tau equals to V q by I b for the entire cross section of the circular cross section of the member. However, we can apply at the neutral axis, wherein the stress distribution is parallel to the y axis, and thereby we can apply this expression V q by I b, and consequently if we compute, the maximum shear stress which we get at the neutral axis is equals to 4/3 V by A, and this again we compute from V q by I b, and q is the moment of the area above the section where we are considering the shear stress, which is neutral axis in this particular case. So, the maximum value of shear stress for the circular cross section is 4/3 V by A, where again A is the cross sectional area of the circular section. And the lastly, we had the question that what is meant by average shear stress. Now, as you can see over the cross section, the distribution of the shear stress, say for example, when we are dealing with rectangular cross section, we have seen that the distribution is a parabolic one and having the maximum value of the shear stress at the neutral axis. Now, many a times if we like to evaluate quickly a value of the shear stress for engineering applications, many a times we need to get a first hand information about the stress, and if we like to evaluate quickly, then instead of calculating this parabolic distribution, many a times we assume that the stress as if is uniformly distributed about the entire depth. And if we consider say this particular stress as the average stress, let us call this as tau average, which has its value uniform over the entire depth. Now, when we do that, we take the area of this particular rectangular configuration, which is uniform over the entire depth, equivalent to the area corresponding to the distribution which we get from 0 to the maximum value. Now, if we say the tau average is this width, the area of this rectangle is tau average times h, and this should be equal to the area under the curve with the actual distribution of the shear stress, which is 2/3 of h times tau max. Now, as we have seen earlier, the tau max is 3 by 2 times V by A, where V is the shear force and A is the cross sectional area. So, this gets cancelled. So, we have tau average into h is equals to h into V by A. So, thereby tau average gives us a value of V by A. Tau average is equals to V by A. Now, where V is the shear force and A is the cross sectional area, and as you can see, we are assuming that as if the stress is uniformly distributed over the entire cross section, and that is why it is called as average. So, shear stress distributed uniformly over the cross section is termed as the average shear stress and is calculated, the shear force divided by the cross sectional area will give us the value of the tau average. So, these were the questions which were posed last time, and these are the answers corresponding to that. Now, having looked into these aspects of the shear stress, let us look into the aspects of the elastic curve based on which we arrive at the differential equation. Now, let us consider a segment of the beam. Let us say this is the origin O along the member axis, beam axis. This particular point is A, which is at a distance of x from the origin. Now, let us assume that this particular beam undergoes deformation in the positive direction. Now, this is the y positive direction, and we assume that the member undergoes deformation in the positive y direction, and after deformation, this is the deformed configuration, and the point A moves to A dash. Now, if you remember, we had said that the beam axis, when it undergoes deformation, it does not stretches. That means, we had looked into while deriving the bending formula that the strain at the neutral axis level is 0. So, we assume that there is no stretching of the axis of the beam. Now, let us assume that this particular point, if we consider a small segment after A, we call this as a distance A B having a length d x, and if we exaggerate this particular figure and plot it over here, it looks like this, that this is d x, this is A and this is B. After deformation, this is A dash and this is B dash. Now, point A has undergone a deformation which is y, which is indicated over here. Consequently, over a small distance dx, the point B has undergone a deformation which is y plus dy. So, this particular stretch is dy. Also, at this point, the deformation, I mean the slope of this particular axis, if we call theta, at this point over the length dx undergoes small change, we call this as theta plus d theta. The radius of curvature of this beam axis is rho. Now, over this particular segment dx, the angle it subtends at the center is d theta. So, if we consider, since our based on our assumption that the beam axis does not undergo any stretching, hence this particular curved part also is dx. So, from this particular triangular configuration, we can say that dy by dx is sin theta, and this is what is written here, dy by dx is equals to sin theta, and theta being small, because we assume that the beam undergoes a very small deformation and thereby the slope is very small, theta is small, hence sin theta can be represented in terms of theta. So, dy dx equals to sin theta is equals to theta. Also, this particular arc length dx can be written in terms of theta as rho times d theta. So, dx is equals to rho times d theta. So, from this we can write that 1 by rho is equals to d theta dx, and in place of theta if we substitute dy dx. So, d dx of dy dx, it gives us d2y dx2. So, 1 by rho is equals to d2y dx2. This is the second order differential of y with respect to x, and this is our curvature. If you remember from the previous module's lecture, that we had curvature is equals to 1 by rho. Hence, now if we write down that 1 by rho, as we have just now seen, is equals to d2y dx2. Earlier, while evaluating the beam bending formula, we have obtained that 1 by rho is equals to m by ei, and thereby if we equate these two, we get d2y dx2 is equals to m by ei, or m is equals to, or ei d2y dx2 is equals to m. This is what we call as the differential equation of the elastic curve. Now, this particular differential equation gives us that how the deflection curve, the beam axis which was straight before bending, after bending it deforms and it takes a shape based, I mean from this particular equation we can arrive at that what will be the shape of this particular deformed axis after it has undergone the deformation. And this particular parameter ei is termed as the flexural rigidity of the beam. Ei is called as the flexural rigidity. Well, now from the differential equation which we have obtained, if we integrate once the differential equation which we have ei d2y dx2 is equals to the bending moment m. Now, if we integrate this, we get this, that ei y dash indicates its dy dx, y dash stands for dy dx. Now, ei y dash is equals to integral m dx plus a constant of integration C1. Now, if we integrate this equation once again, so second integration yields that E I y is equals to double integral m dx over dx and plus C1 x plus C2, where C1 and C2 are the unknown constants, and these constants are to be evaluated from the given boundary conditions or known boundary conditions of the beam. Now, from these, in fact, we can write y as a function of x, because moment is a function of x in the beam, as we have seen in the past, and y can be evaluated along the length of the beam. So, at different point we can get the value of y, and if we plot that, if we plot the value of y along the length of the beam, that gives us the deflection curve or the elastic, the movement of the elastic curve. Now, this particular expression we call as the equation of elastic curve. So, as we have seen now that we have first derived the differential equation of the elastic curve, and subsequently now we have computed the equation of the elastic curve. Now, making use of this differential equation, which is written as a function of the beam bending moment, now we can compute the value of the or the equation of the elastic curve, or we can compute deflection at any point along the length of the beam. Well, now if we look into the aspects whatever we have evaluated so far, y gives us the deflection of the elastic curve, theta, which is the first derivative of y, which we call as y dash, gives us the slope of elastic curve. That means, if we have the beam, if we have the deflection of this form, then if we take a tangent at any point on the elastic curve, this gives us the value of the slope theta, which is dy dx, the derivative of the deflection curve. Second derivative subsequently give us the value of the moment, which is the differential equation for the elastic curve, that E I d2y dx2 is equals to the moment. Now, in the previous lesson we have seen that the shear force V is equals to the rate of change of the bending moment with a negative sign. So, V is equals to minus dm dx, and m, as we have seen in terms of this differential form, as E I d2y dx2. So, this is minus d dx of E I d2y dx2. So, this gives us that minus E I d3y dx3 is the value of the shear, or E I d3y dx3 is equals to minus V. And also we have seen that q is equals to dv dx, and if we substitute for the v, which is the second derivative of this moment, gives us the value of E I minus E I d4y dx4, this is equals to the loading q, or E I d4y dx4 is equals to minus q. So, these are the different forms of the governing equation, governing differential equation, which we have obtained, that E I d2y dx2 is equals to moment. From this we can derive the other relationships as well. Now, as we have looked into now that E I d4y dx4 is equals to minus q, this is the differential equation if we write in terms of load. We have seen that the differential equation in terms of the bending moment, which is E I d2y dx2 equals to m. Now, also we can write E I d4y dx4 is equals to minus of the loading q. Now, if we integrate this, we get E I d3y dx3 is equals to minus q dx plus C1. Now, if you remember, E I d3y dx3 is nothing but equals to minus V. So, minus V equals to minus q dx plus C1. Now, this if we write as equals to q dx, now minus C1, now this is being constant, we can write this as a modified form, say C1 hat. Now, V equals to q dx plus a constant, this expression we had seen earlier when we had evaluated the shear force and the bending moment, and there you had looked into that q is equals to dv dx, and thereby V was integral q dx plus a constant term. Now, when you are, so this particular expression we had arrived at from the equilibrium of a small section which we had taken out from the whole beam. So, this particular expression represents the equilibrium of the loading system. Subsequently, in fact, we have seen that the moment is dm dx, the derivative of the moment is equals to shear, V equals to minus dm dx. So, if we compute that from this particular expression, we can get m as integral of q dx plus c 1 x plus c 2, and this is what is over here, and this is our moment E I d 2 y dx 2, and hence this particular set of equations represents the equilibrium of the beam segment, and further integration of these gives us the value of the slope and corresponding deflection. Now, if you look into the constants which are associated with this particular set of equations like C 1 and C 2, these can be evaluated from the boundary conditions of a beam from the known values of the shear and the moment, and we call that these particular constants can be evaluated from the static boundary conditions. So, this is what is written over here, that C 1 and C 2 we can compute from the static boundary conditions. Now, for this dy dx and y, we have the constant C 3 and C 4, and these constants C 3 and C 4 are evaluated from the relationship of the deflection and the slope of the beam, and these boundary conditions are called as the kinematic boundary conditions. So, C 3 and C 4 are evaluated from the kinematic boundary condition. So, you see that there are two sets of boundary conditions which we need in fact for evaluation of these unknown constants. They are the static boundary conditions or the kinematic boundary conditions, and this kinematics in a sense that after the deformation of the beam it undergoes movement and it has some slope and the deformation, and those boundary conditions if we adopt, we can evaluate the value of C 3 and C 4. Well, let us look into the boundary conditions that we come across. Now, if we have a fixed support for a beam, now at this support, as we have seen in the earlier lessons, that it does not allow any movement. So, the deformation or the displacement of this particular point is 0, and consequently it does not allow any rotation as well at this point, and hence the dy dx or the theta also is 0, and both the conditions are the kinematic conditions. In a hinge support or a roller support, we know that the vertical displacement is constrained and thereby y is 0, and also at a hinge support it cannot resist any bending and thereby it gives rise to the slope. So, we have the bending moment at this point equals to 0. So, for a hinge or a roller support, we have the vertical displacement is 0, which is a kinematic condition, and the moment equals to 0, which is a static boundary condition. And for a free end, since it undergoes both displacement as well as rotation, now here we have the boundary conditions which are basically static boundary conditions, the moment equals to 0 and the shear force equals to 0 at this particular point. So, these are the different support conditions which we have seen in the past, that a beam is supported on some supports. So, these kind of supports could be fixed support or hinge support or roller support, or it could be free on one end and fixed at the other, as we have seen in case of a cantilever beam. So, any combinations of these supports give us the appropriate configuration of a beam, and when such beams are loaded they undergoes deformation, and because of those deformation we need to evaluate now what will be the deflection and the slope because of the loading. Now, in this particular case, while deriving the equation for the elastic curve, we have considered that the deformation is a small one, and thereby we said that the axial axis of the beam, when it undergoes deformation, does not stretches, the length dx remains dx. But supposing if we have a very large deformation of the beam, if the deflection is very large, then we cannot make these approximations, and thereby the curvature term, that 1 by rho, takes this particular form, and the whole form has to be taken into account for evaluating the differential equation for the elastic curve. Hence, the expression which we have derived here, they are suitable for small deformation only, and for large deformation this is not applicable. We will have to use the curvature in terms of these expression. We are not going to the detailed derivation of this, but for your information that for a large deformation of the beam, the curvature term is to be used with this particular expression. Well, let us look into the sign convention once again, so that we get acquainted with the when we will deal with the problems, you do not have any problem as such. Like we had considered for a beam segment, this is a beam segment having with dx and loading on this as q. On the right hand side we have the shear force which is pointing upwards to the positive y direction, and on the left side we have downward as the positive shear, and this is the positive bending moment which is in an anti-clockwise form on the right hand side and a clockwise form on the left hand side. And consequently, we had obtained the relationship which is V equals to minus dm dx and dv dx equals to q. Now, these relationships we have used while deriving the differential equations and its different form of the governing differential equation. We have used E I d2y dx2 equals to bending moment, and subsequently when we have taken the derivative, we have taken that dm dx as minus v and dv dx as q. So, this we have used while deriving the different forms of the governing equation. Now, here, so to remind that again, so E I d2y dx2 is equals to moment, considering the moment positive as anti-clockwise on the right hand side. Now, E I d4y dx4 is equals to minus q. Now, please note over here that the loading q, which is in fact in the opposite direction of our positive y axis. Y axis positive is upward. So, any loading if it is directed upward is positive, and since this q is pointing downwards, so q is negative, and rightly that we have E I d4y dx4 is equals to minus q, and also we have E I d3y dx3 as minus v with the positive shear pointing upward. So, these are the expressions which we use for evaluating the equation of the deflection curve y. Now, E I d2y dx2 equals to m and E I d4y dx4 equals to minus q, these are the two expressions which are widely used. We do not use this particular expression very frequently, which is E I d3y dx3 equals to minus v. However, any of these three equations can be used for evaluating the equation of the elastic curve, which is y as a function of x we can evaluate, and thereby at any point along the length of the beam member we can compute the value of y, and thereby the plot which we get will give you the elastic curve or the deformed shape of the particular beam after it is loaded. Well, having looked into these equations for the elastic curve, let us look into some example problems. Now, before we go into the example problems of this particular aspect, let us look into the example which I had given you last time, which is related to the evaluation of the shearing stress. Now, if you remember that a beam of T cross section is formed using nails as shown in the figure. Now, here there are two rectangular components, one is a horizontal one, another one is a vertical one, and these two separate units are joined together by providing a nail along the length of the beam, and the nails are provided at an interval. Now, the shear force which is acting in the section is 872 Newton, and the nail carries 400 Newton in the shear. Now, at this interface where two blocks are getting connected together by nails, and this nail when it will be subjected to a shearing force, it will be subjected to the shearing action. Now, this nail has a resistive power, it can resist 400 Newton of shearing load. Now, we will have to find out that at what spacing of these nails along the length of the beam we can provide, so that it can withstand that amount of load. That means, the shear force in each nail should not exceed the allowable limit. If it is less than that, then it can withstand that load. So, that is the aspect you will have to evaluate, what is the maximum spacing, allowable spacing of such nails. Well, this is an interesting one. Let us look into the aspect here. Now, in this particular figure, we have separated out the wave part of the section. This particular part is shown over here. Now, this is the face of the beam cross section. Now, here the positive shear is acting in this particular direction, which is positive upward. Now, we have the complementary shear which is acting on this face, perpendicular face, which is acting in this form, and this is what is shown in over here, and of course, we have the shear in other direction as well. Now, along this length of the beam, these are the nails which are placed, which are spaced at a spacing of p. So, if we can compute the level of shear stress that is acting at this particular level, then we know how much shearing stress will be acting at this face, and once we know the shearing stress on this face, we know how much shear force this particular bolts are to be resisted in terms of the shearing stress. So, if we like to compute the shearing stress at this particular cross section, then we need to take this particular area which is above this section and take the moment of this area with respect to the neutral axis. Now, so first we will have to find out the position of the neutral axis of the cross section, and if we say that this is y bar from the top, then take the moment of all these segments with the top part of it. So, first segment is 120 by 30. So, 120 by 30 into 15 is the moment of that area with respect to the top line, plus the area of this bottom part, the wave, is 120 times 30 times this is 60 plus 30 is 90, divided by the area of the whole cross section, which is 120 times 30 plus 120 times 30, and this gives us a value of y bar equals to 52.5 millimeter from the top. Now, we got to evaluate the moment of inertia of this particular cross section with respect to the neutral axis. So, I neutral axis, again we compute for, we divide the whole of the cross section into two rectangles. The first rectangle 120 by 30, it has moment of inertia about its own axis as 120 times 30 cube by 12 plus 120 times 30 times its distance, its CG distance from the neutral axis is 37.5, 52.5 minus 15 square, plus for this is 30 times 120 cube by 12 plus area 120 times 30 and 60 plus 30 90, 90 minus 52.5 will give you 37.5 square. So, this is the moment of inertia of the section, which is 14.715 into 10 to the power 6 millimeter to the power 4. Now, from the expression of tau equals to V q by I b, V in the section is given as 872 Newton. Now, q is the moment of the area above the section where we are evaluating the shear stress. We are evaluating shear stress at this section, and the area above that is 120 times 30. So, 120 times 30 and its neutral its CG is 15 from the top, and distance of the neutral axis of its CG from the neutral axis is equals to 37.5, 52.5 minus 15 divided by I, and B here is 30. So, this gives us a value of shearing stress at this interface. So, along this length we have a shear stress of 0.27 Newton per millimeter square. Now, if these nails are spaced at p millimeter apart, then if I consider this particular nail, it has an influence area half of this length and half of this length. So, this much of length multiplied by this width, width is 30 multiplied by p. So, that is the area multiplied by the shearing stress that is acting at that interface will give the force that this particular nail can withstand. And since a nail can withstand a maximum shear force of 400 Newton, if we equate to that, we get a value of P as equals to 49.4 millimeter. So, that means this particular nails can be spaced at a maximum distance of 49.4 millimeter. We can keep a lower value than 49.4 millimeter, but we cannot exceed this particular, that is the maximum value of the spacing of the nails that can be provided, so that the shear stress in the nail does not exceed 400 Newton. Now, if we go beyond that, then the shear stress, I mean the shear capacity of the bolt will go beyond 400 Newton, and as a result the bolt will not be able to withstand and the cross section and the whole section will fail. So, this is the value of the spacing of the nails that are to be provided, so that the member becomes safe. Well, that was the problem for the shear stress. Now, let us come back to this the equation of the elastic curve. Now that we have a simply supported beam which is subjected to a uniformly distributed Q per unit length. Now, what we will have to do is that we will have to determine the equation of the deflection curve. This is the first thing we will have to do. This is number 1. Secondly, we will have to find out the maximum deflection and the rotations at the supports. Now, the flexural rigidity EI is constant for the entire beam. So, we will have to determine the equation of the elastic curve, and secondly the maximum deflection and the rotations at the support points. So, to do that, then let us first evaluate the reactive forces as we have done in the past. Now, as you know, this is a hinge support. So, you have the vertical support and vertical reactive force and the horizontal reactive force, and this being a roller support, you have a vertical reactive force. So, if we call this as A, this as B, then this is R A, this is R B, and this is H A. Now, since there are no horizontal loads in this beam, so summation of horizontal force equals to 0 will give us that H A is equals to 0. Now, we will have to compute the value of R A and R B, and as we have seen in the past, this is a symmetrical beam subjected to a symmetrical loading. Hence, the value of R A and R B is equals to Q times L by 2. This is the total load. Now, this we can compute from R A plus R B equals to total load Q L, and if we take the moment of all the forces with respect to one of the supports, you get the value of R A, and then you can compute from the vertical equilibrium the value of R B, and you will get the value of R A and R B as equals to Q L by 2. Now, let us employ the differential equation of the elastic curve as we have derived now. Now, so we have the beam in which we have evaluated the value of the reactive forces R A and R B, and this we have seen as equals to Q L by 2, and Q is the uniformly distributed load that is acting on the beam. Now, if I take a segment at a distance of x, a free body of this particular part will yield that you have the reactive force R A here, you have the Q, and on this cart we will have the shear force V and bending moment M. These are the positive direction of V and M as we have seen. Now, if we compute, if we take the, this is the value of Q. Now, if we take the, and this mind that at a distance of x from A. Now, if we take the moment of all the forces with respect to this particular point, then we write M, which is in an anticlockwise direction, then minus R A into x minus, this is minus, and Q cause a moment which is anticlockwise. So, plus Q into x by 2, this is equals to 0. So, the value of bending moment M is equals to R A is Q L by 2. So, Q L by 2 x minus Q x square by 2. So, this is the value of the bending moment that we have. Now, as we have seen that E I d2y dx2 is equals to bending moment M. This is our differential equation for the elastic curve. Since we are going to find out the equation of the elastic curve, we start from this particular point, and as we have seen now m is equals to q l by 2 x minus q x by x square by 2. So, this is equals to q l by 2 x minus q x square by 2. Now, if we integrate this, we have E I dy dx as equals to q l by 2 times x square by 2 minus q by 2 x cube by 3 plus C 1 is the constant of integration. Then further if we integrate this, we have E I y as equals to q l by 4 x cube by 3 minus q by 6 x 4 by 4 plus C 1 x plus C 2. So, this is the equation of the elastic curve with the unknown constant C 1 and C 2. Now, we will have to evaluate the values of C 1 and C 2 with the help of boundary conditions. Now, what are the boundary conditions we have for the simply supported beam? Now, if we look into the deflected profile of this, the beam is going to, the curve which we have the axis is going to deform in this form. Now, at since this is hinge support and this is roller support, at x equals to 0 the deflection is 0 and also at x equals to L y is equals to 0. So, these are the two conditions we have. Now, if we substitute these conditions, you see the first of the conditions at x equals to 0 y equals to 0, if we substitute in this equation, we find that C 2 is equals to 0. So, now that if we substitute the second condition that at x equals to L y equals to 0. So, if we substitute over here for x we substitute the value of L and y as 0 and then consequently let us see what we get. We get 0 as equals to q L by 12 and we have L. So, L cube minus q by 24, you have L to the power 4 plus C 1 times L. So, this gives us a value of C 1. Now, if we compute this, we get C 1 as equals to minus q L cube by 24. So, the equation of the deflection curve E I y, this is equals to, we get as q L by 12 times x cube minus q by 24 times x to the power 4 minus q L cube by 24 times x. So, this is the value of the, or this is the expression of the elastic curve for the beam. So, at any point x we can get the value of y. Now, if we like to compute, now as you can see that we have the beam and we have now the expression for y, at any x we can compute the value of y. Now, since this particular beam is symmetrically loaded with uniformly distributed load, now it is expected that we will have the maximum deformation at the center. Now, if we compute the value of the deflection at the center, that means, if we compute y at x equals to L by 2, let us see what we get the value of y as. So, E I y as equals to q L by 12. Now, this is L cube by 8 minus q by 24 times L 4 by 16 minus q L cube by 24 times L by 2. So, this gives us a value of, if we compute this, this comes as an expression of q L 4 by 96 minus q L 4 by 384 minus q L 4 by 48. and if we compute this, it comes as minus 5 q L 4 by 384. Now, in fact, this is the value of the deflection. So, y at L by 2 is equals to minus 5 q L 4 by 384 E I. Now, taking E I on the other side. So, this is the value of the deflection at the center of the beam. Now, here you note that we have a sign which is minus. This indicates that our positive y direction is upward, hence the deflection curve is towards the downside of the beam axis. So, this is the deflected shape of the beam. This is the y at L by 2. So, it goes from 0 here, goes to L by 2, from here again it goes here. So, the value here which we call as the maximum displacement delta max as equals to 5 q L 4 by 384 E I. Now, once we have the expression for the deflection curve E I y equals to this, now we can take the derivative of this and can compute the value of the slope at this point, or we have already have the expression for the dy dx which is this, and as we have seen that the value of C 1 we have already obtained. If we substitute over here, we can get the value of dy dx. So, we can compute the value of the slope at x equal to 0 and at x equals to L. Now, let us compute the value of the deflection, I mean slope at the support points. So, this is the value of the deflection that we have obtained. Now, if we compute the value of dy dx, this is of course E I dy dx, we are taking the derivative of that. So, this is q L by 12. So, this is 3 x square minus q by 24, this is 4 x cube minus q L cube by 24, because the x goes off. So, this is the value of E I dy dx, and dy dx at x equals to 0, since these are a function of x. So, this goes off. So, we have minus q L cube by 24. Now, here if you note it, again this is given as negative. Now, here this is the deflected curve as we have obtained. Now, if we take the tangent of this elastic curve at this particular point, then this curve with this rotation is in a clockwise direction. So, this particular rotation is in the clockwise direction. Now, as we have seen that in a beam segment, when we consider the positive bending moment, that is in an anti-clockwise direction, and consequently, since this is in a clockwise direction, we say this theta as negative, which is clockwise. Now, if we compute the value of the rotation at the other end at x equals to L, then in this particular expression if we substitute x as L, then let us see what we get the value as. Let us compute the value of dy dx at x equals to L. So, E I dy dx, this is equals to, now this is L square. So, q L cube by 4 minus this is L cube. So, this is q L cube by 6 and minus this is q L cube by 24. So, we have 6 minus 4 minus 1 by 24 times q L cube. So, here you get this as q L cube by 24, and mind that here we get positive. Now, here if you look into, if you take a tangent at this particular point, the rotation here again is an anticlockwise direction, and according to our nomenclature or the sign convention, this is positive. So, theta b is equals to plus q L cube by 24. So, we have theta a computed, the theta at support A and theta at support B. So, these are the aspects we were required to compute we have computed first the equation of the deflection curve, and consequently we have computed the deflection at the center of the beam, which is the maximum deflection in this particular case, and consequently we have computed the value of the rotation at A and B as the support points. Well, let us look into, so this is the final form of the deflected form of the beam, that when it is loaded you have the deflected curve, and this is the maximum deflection which we have at the center, and this rotation we have obtained as theta A, which is negative, and this rotation is theta B, which is positive because counterclockwise, and this is the shape of the deflection curve. Now, if we look into the another problem where the beam supports are identical, that means we have a hinge support over here and a roller support here, but instead of a uniformly distributed load we have a concentrated load P, and to make this evaluation of the deflection curve and to evaluate the deflection, a general one, the load is placed not symmetrically, but in an unsymmetric form. The load is located at a distance of A from support A, and it is at a distance of B from support B, and the length of the beam or the span of the beam is L. Now, what you will have to do is that you will have to evaluate the equation of the deflection curve, and you will have to evaluate the maximum deflection. Also, you will have to find out the rotation at the support. Now, flexural rigidity of the beam E I is constant throughout the beam. Now, as usual what we need to do is the hinge support you will have the vertical reactive force and the horizontal force, and a roller support will have a vertical force. So, we call as usual this as R A H A and this as R B. Now, H A will be equals to 0 as we do not have any horizontal load in this beam. Now, if we take the moment of R A or the moment of R A and the load with respect to B, then we have R A into L is equals to, which is in a clockwise direction, and P times B is an anticlockwise direction. So, R A is equals to P B by L, and since R A plus R B equals to P, so R B will be equals to P minus P B by L. So, that is equals to P A by L. So, these are the values of the reactive forces R A and R B. Now, here you look into that we have two segments, this is segment 1 and this is segment 2, and in these two different segments our bending moment expression will be different. So, now let us compute the value of the bending moment for these two segments. Now, we have the beam, this is R A and this is R B, and you have the load here as P. Now, for the segment 1, if I take a free body here, if I take a cut here and draw the free body diagram, then the bending, this is the shear force, this is the bending moment M, and this distance is at a distance of x from the support A. So, the bending moment M is equals to R A times x, which is equals to P B x by L, and the validity of this particular moment is from this particular point up to the load point. So, the validity is 0 less than x less than A. Now, if I take a free body of this particular segment, taking a cart over here, if we take the free body of this particular part, then we have the reactive force here, the load here. Now, this is at a distance of A, and the segment we have taken at a distance of x from the support, and as usual you have the shear force and the bending moment over here, and let us call this as moment M, and this is P. So, the moment expression which we get at this particular point is equals to M is equals to, this is R A into x minus P into x minus A, and R A being P B by L. So, this is P B x by L minus P into x minus A, and the range of the validity of this is A less than x less than L. So, these are the two moment values that we have. Now, once we get the expression for the moment, then we can write down our differential equation, which is E I d2 y dx2, this is equals to moment, and we write for the two segments differently, that for the segment 1 this is the expression for the bending moment, for the segment 2 this is the expression for the bending moment, and consequently we integrate it one by one, and then in the first step of integration we get dy dx, and in the second step we get y, and that gives us the expression for the deflection curve. Now, once you solve this, since we have two different segments and two different equations, so thereby you will be land up with 4 unknown constants, and these 4 unknown constants are to be evaluated from the 4 unknown known boundary conditions. Now, this problem is set for you, look into it. We will discuss how to solve those unknown constants and how to arrive at the deflection curve in the next lesson. Well, to summarize then, in this particular lesson we have included the concept of deflection of beams for different loadings, and of course we have discussed the previous lessons some aspects as well. Then we have looked into the derivation of the equation of elastic curve, the differential equation first we have derived, and consequently we have derived the elastic equation for the elastic curve. Then we have looked into some examples to how to evaluate the deflection of beams for different loading. Now, these are the questions set for you. What is the differential equation of elastic curve in a beam? What is the equation of elastic curve of beams? And what is the value of maximum deflection in a simply supported beam subjected to uniformly distributed load of intensity W? Now, answers for this I will give you in the next lesson. Thank you for your attention. Welcome to the second lesson of the 7th module, which is on deflection of beams part 2. In the last lesson we have introduced the concept of deflection of beams, and also it has been introduced that how deflection of beams plays an important role in the engineering structures. We have derived the equation, the differential equation for the elastic curve, and subsequently we have derived the equation for the elastic curve, and we have seen that how to compute the deflection of beam at any point for a particular kind of loading. Now, in this particular lesson we will be discussing some more aspects of the deflection of beams for different types of beams and subjected to different kinds of loads. It is expected that once this particular lesson is completed, one should be able to understand the concept of deflection of beams under different loading conditions for different types of beams. In fact, last time we had looked into simply supported beam subjected to loads. Here we will be looking into some more types of beams with different kinds of loading systems. One should be in a position to understand the concept of superposition method. We will discuss this particular method, the superposition, how to evaluate the deflection if you have more number of loads which are acting simultaneously in a beam.